All right, welcome back. In the last video, I said that was the last video for this week. I lied unintentionally, so I am sorry. Yesterday, I was making some kombucha and some bread, and I had a bit of downtime, and I thought, you know what, it might be helpful to kind of go over a bit of what we've done this week and last week and before the test, and show how all of that relates and how all of that is kind of intertangled. And then I was like, I'm also just going to make them a little bit of a roadmap to kind of organize these ideas, organize the processes, so nobody is kind of left in the dust, right? Because this is a lot of information. So much of it is very similar, right? So I want to kind of differentiate these things just to make your life a little bit easier. So this is a Carson Keeter kombucha idea, so let's just get into it. We'll start with a terminology recap. Okay, so we have these three ideas, right? That we've seen confidence intervals and test statistics last week, right? This idea of degrees of freedom is a little bit new to us, and that's okay, right? But in fact, this idea of a test statistic, we've been doing this since before the first test, right? A test statistic is really just a fancy word for essentially a z-score. Okay, now hold on. It's not totally the same. But the idea is there, right? Very similar. So before the test, right, we are calculating these z-scores, essentially telling us how far away one person was in our data away from the mean, right? So if we calculated a z-score for somebody and that z-score was 2.5, that means that this one person was 2.5 standard deviations above the mean. Okay, we do it again for someone else, and it's -1. That means that they are one standard deviation below the mean. Okay, and we're able to kind of figure out relatively where everyone stands, right? Centered sort of around 0, right? Because you can be right at the mean too, and that's okay. That would result in a z-score of 0. Okay, fast forward just a little bit to this idea of a test statistic, where we are essentially doing that same concept, but for our whole data set, right? And essentially, that test statistic just tells us how far away we were from our expected spot, okay? And that's all done in standard error units, very similar to standard deviations, right? So if we calculate a test statistic for our data, and it might be, I'll write this out, maybe t equals, 1.8, whatever. That means that we were 1.8 standard error units away from where we expected the data to be, okay? And so the bigger this value is, the further we are. So if we got like 8, right? If we got a t-value of 8, that means that we are further away, or farther away. Further or farther? Oh boy. Whatever, you get it. 8 standard error units away from our expected value, right? Or we are that far away. We are that far away from where we expected our data to be, right? And this is all tying back to that idea of the central limit theorem. And if that's totally over your head, that's totally fine, right? But the idea here is that this just tells us how far away we were from the expected spot, okay? So a high t-stat, or a high z-score, even when we were doing the stuff in the z distribution, right? Either a high z-score, a high z-score, or a high t-stat means that we are further away from our expected value, right? Our data is very far away from where we expected it to be, which then results in a low p-value, right? Which then tells us that our observed data, the data that we have, is unlikely due to random chance, right? Okay, and that we can say that is a statistically significant result, right? Whatever we're measuring, whether it's a difference or a mean or whatever, right? The opposite is true as well. So low t-stat means that we are very close to where we expected our data to be, right? That means that our p-value is going to be high. That means that whatever we saw, whether it was above or below the mean, or above or below the known proportion, whatever it may be, that means that even though it was above or below, it's probably just due to random chance, right? We had a sampling thing, right, that was going on in the background that we didn't really see, right? So that results in a statistically insignificant result, whatever, right? So the test statistic, the long and short, just tells us how far away we were from our expected value. Okay, sweet. Degrees of freedom. Now, we can talk years about degrees of freedom. It's a big thing, right? It's a big thing. But essentially, it just boils down to the amount of independent information we have, right? So when we calculate the mean, right, we just took up one bit of independent information, right? And then that just leaves, we only need n minus 1 things to figure out that last value, right? We can go back to that example that I gave with the Seinfeld gang, where they're all worried about getting their credit card information stolen. As long as the mean is unknown, right, then all of their information is totally fine, right? But when the mean is known, that used up a bit of independent information, and that makes it a little bit closer to figuring out what that last value could be. Okay, and then the t-distribution. The reason why we work with the t-distribution is because we don't know what the population standard deviation looks like. We don't know what the population looks like, which is very common, right? Super common. So we estimate the population standard deviation with S, with our sample standard deviation. But because we do that, that means that our distribution is going to be a little bit fatter with the small, It's going to be a little bit fatter with the smaller sample size. But then it turns out that as the sample size increases, it starts to look more normal, which is very helpful. It's all a function of as the sample size increases, we get a better idea of what the population might look like, because we start including more of the population, whether we know it or not. Okay. And then lastly, the confidence interval here is just a range of values that we're able to calculate that may contain the true population parameter. Okay, a little fancy statistical term here just for what we've been doing, right? It could be a proportion, it could be a mean, it could be a difference in means, right? It could be anything. We can make a confidence interval for literally anything. You just have to know the standard error formula for that, right? And then depending on where your information came from, the critical value too. Whether it came from a normal distribution or we're using a t-distribution. There's a bunch of other types of distributions out there that we're not going to worry about. They get super complicated very quickly. But that's the general idea, right? We're able to estimate where the actual population parameter may be. And we limit ourselves, though, to some level of certainty, right? So typically we make a 95% confidence interval, just meaning that if we were to do some experiment, 100 times, then 95 of those times, the thing that we're measuring will be within this range of values. Within this range of values here, right? And then the higher our confidence level is, that range of values gets wider because we need to include more so we can be certain that the right value is somewhere in there. Right? And then as the confidence level decreases, right? As the confidence level decreases, that means that our interval is going to become narrower, right? Because we're less certain that we got it, right? We might have hit the bullseye, right? But we're also leaving more up to being wrong. Okay, so that's the general idea with the concepts that we have learned pretty much starting at week 2, which is crazy, right? Super crazy, I think. So it all ties back together, right? It all ties back together into this beautiful painting. Kind of like a Bob Ross thing. I'm not suggesting that I'm the Bob Ross of statistics, not even close. But actually, if you want, you can take more classes in the stat department with people who are like the Bob Ross of stats. People who have years of experience, which is pretty great. We got a good program here at the old University of Wyoming. Okay, so I think that's everything that I want to say about that. Let me then buckle up because I'm going to show you a bit of a roadmap. Okay, so this is for t-tests. T-tests. Okay, so here it is. You can kind of think of this as like an algorithm, or just like a choose your own adventure kind of situation. But the first question should be, I don't know what t-test to use. Okay, well then all you got to ask is how many groups are there? What are you doing? Okay, we'll start over here with one group. Okay, so if there's only one group, then the only option you have is to do a one sample t-test, right? So with all of these, we'll take a step back. With all of these, you can't just choose which one you want to do, right? You have to specify some criteria, right, to make sure that the test you're doing is appropriate, right? So you can only do a one sample t-test if you only have one sample, right? And then an independent t-test, you can't just choose to do a paired t-test, right, if your data aren't paired. So it's all about what your data look like and not what you want to do, okay? So anyway, we got one sample here, come down here to do a one sample t-test, right? And that's against some known value. So the t-statistic is right here, right? This is super familiar. The mu naught, right, is always going to be specified, okay? Or 0 if paired. We'll get back to that. That's a new concept that we haven't really talked about. We'll come back. Degrees of freedom, just n minus 1, right? Confidence interval, it's all right there, right? You find your t-crit by going to that tool, right? Plugging in your alpha, plugging in degrees of freedom, and then you're set. You find some value, right? And that's that. You get some result. Easy peasy, right? Okay, and then we come over here. What if you have two groups? Well, then you got to ask a new question, right? Were they measured? Were these two groups measured at different times? As in, is it the same group at one time point and then the same group again later, right? If that is true, then you come over here and do a paired t-test. Now, you'll notice here that I've got this dotted line kind of separating these things, but a straight line here, a straight black line here, denoting that these two are totally separate, right? So the concepts are the same, right? But you can't do one in place of the other. However, a paired t-test can be, as far as function goes, replicated with a one sample t-test. Well, let's come back to that. So if your data are not paired, right, which is frequent, and that's okay. So no, right, the data are not paired. Then you do an independent t-test, right, comparing two separate groups, right, that are not related. They are independent of each other. Okay, you've got your test statistic here. You just take the mean of your first group and subtract it from the mean of the second group, divided by the square root of, and then the sample variance here divided by the sample standard, the sample size, right, of the first one, plus the sample variance of the second group divided by the number of things in the second group. Easy peasy, right? And that gets you some t-stat. You throw into the calculator there, and you get a p-value. Okay. Degrees of freedom, a little different than the degrees of freedom over here. You just take the smallest. So if you have two groups, and one of them is smaller than the other one, you take that n to calculate the degrees of freedom. Okay. Sometimes though you have the same number. And that's totally fine. So if you had 10 in each group, so a total of 20, right? Well, you just take 10 minus 1, that's 9. So you'd have 9 degrees of freedom. Easy peasy. Okay, and then the confidence interval you can see there, right? You just take the difference of the two, right? This, you can also say this is like xd or whatever. So this is just going to be some value, some difference between the means, right? And then the t-crit and then the standard error, right? And notice that the standard error is also down here, right? Easy peasy. So you could take this whole thing, right, and into the test if you wanted, and you're pretty much set, right? You could plug and chug if you needed to. Okay, don't do that. I hope you get the concepts too. But if it really boils down to that, then here you go. Okay, data is paired. Well, oftentimes for a paired t-test, the standard error formula down here is a pain in the ass to calculate. It's something new that we haven't done, so I'll just give it to you. Okay, I'll give it to you. So d bar is just the difference of the means, right? That's the same way as calculating this, no biggie. But the sample standard deviation of the difference is not easy to calculate. At least I don't care that you know how to calculate it, okay? Because, well, there's a simpler way to do it if these aren't specified. But again, we'll come back to that in a second. Okay, degrees of freedom is just the number of pairs minus 1. So if you have, let's see, 10 people measured at 2 different points in time, there are 10 pairs, right? So that means that your degrees of freedom would be 9, right? 10 minus 1 is 9. And then the confidence interval, right? D bar, that's something you've already calculated up here, or it's given to you. And then plus and minus the T crit, found in the same way that we've done this one, and I guess kind of this one too. And then the standard error formula is right there. Just the denominator of our test statistic, right? Sometimes, you don't have to do this every time, but what I like to do is calculate this just separately on its own, and then just plug in the value when I'm calculating the test statistic. And then I've got it for later too, right? Oh boy. Okay, so 1 sample, 2 sample, paired. Those are the 3 types of t-tests. And that's pretty much that. But we've got some similarities between these two that we can talk about. Now, here's the situation. Is that this was introduced to me in a graduate level stat class, okay? And I don't think, though, that it should have been. I think that we could have gotten it in like an intro level stat class. No biggie. So I'm going to try this now, and it's okay if you don't totally get it because, whatever. Oftentimes this will be the situation anyway. But let's just see what we can do in relating these two. Okay. So with a paired t-test, we're looking at differences, right? Always looking at differences with the 2 sample with the paired t-test, okay? But what we're doing with this 1 sample t-test is we just have 1 column of data, right? And we can calculate the mean, calculate the standard deviation fairly easily. And then this is a value that's given to us, this mu naught. In fact, I'll just do this. Okay. So this mu naught is a value that's given to us. Well, what if we have, I'm going to give us 2 columns. Good Lord. I'm struggling here. Let me do it like this. So we have 2 columns of data with 2 observations in each, okay? This is time point 1, and this is time point 2, okay? What am I going to do in this 3rd column? I'll let you know in a second. So let's say that we're measuring something and it looks like this, right? This is our data from the 1st time point and then our data from the 2nd, right? Whatever. Okay, what if I just took the difference between these two? So T1 minus T2. Okay, well that would be -2, and that would be also -2. Cool. Hope my arithmetic there is correct. But now I have this new column of data, right, for the difference. Okay. Well then, traditionally what we would do with a paired t-test is then draw another column out here to square this, and then draw another one to do all sorts of other stuff to it. No big deal, right? Well, I don't want you to do that. I don't want to do that because it turns out to be a simpler way. If we just took this 1 column of differences here and treated it as its own sample, right? As its own 1 sample, right? And we're trying to essentially test if there is any difference between these two, right? Our null hypothesis for this is that the first group, right, equals the second group, right? Which you can also kind of translate into mu1 minus mu2 equals 0, right? We're comparing these 2 groups to see if they are 0, right? If the difference between the 2 is nothing, right? Essentially saying that they are the same. Well, why don't we just take this value 0 here and use that as our null mean, right? So we would take then this difference that we calculated as its own column, right? Take its mean, right? So that would be -2. Plug that in over here, so it'd be like -2 minus 0, right? Divided by, and then we would just calculate the standard deviation for this single column that we have here, which in this case would be 0, because they both don't deviate away from the mean, divided by the square root of 2, right? That would give us some test statistic, which would be -2, because I'm making the math easy for me. And then we can just do a 1 sample t-test based on this single column of differences that we have here. The math does not differentiate between, the math doesn't know, right? We know, but the math doesn't. So we can treat this 1 column here of differences as its own thing. Pretty cool. Okay, so instead of me sort of rambling on here, let me show you another little roadmap here. Okay, and I think that's all I have. Yeah, it is. Okay, so we've got this paired data here. Paired data. Oops. Paired data. Oftentimes, the mean difference and the standard deviation of the difference is given to you. It's specified, or at least I will do that in this class. So then all you want to do is plug and chug, right? For this idea of a paired t-test, right? This is the paired t-test here, gracefully written. Okay, so then you just plug in d bar and s sub d into here, and then do what you normally do for a paired t-test. We've seen that before, and then you get some result. Okay, no biggie. Okay, but then let me zoom in here too. Sometimes d bar and s sub d might not actually be specified. This means that what the heck? Gosh, my phone is blown up. I'm just so popular. Just kidding, it's my mom. Anyway, so if d bar and s sub d, the standard deviation of the difference, is not specified, that usually means that you have data that is, right? Data that's supplied, we'll say. Okay, so no biggie there. So let's say that then we have some columns of data at time point 1 and time point 2. Okay, and I don't know, these could be any values. I'm just gonna use little dots here as placeholders for values. With 2, it gets kind of clunky. Okay, so this is our data set. Okay, no big deal, right? So what do I do in this case? We know that the data are paired, but I'm not given d bar or the standard deviation for the differences, right? And we know, well, you don't, but I do, that doing this is a little difficult, time consuming, and not totally necessary because we have this other way of doing it. So what the heck do I do? Okay, well, step 1 is calculate the individual differences and place them into a new column. So let me actually do this. I'm using these different colors to represent values, okay? Okay, so what do I want to do? I need to calculate the individual differences. Okay, so it looks something like this. So this is going to be okay, I guess this is going to be T1 minus T2, whatever. The order does not really so much matter. So look at this. Color coding here. This is not statistics, right? But with colors and everything. But we see what's going on, right? We're taking the difference between this column and this column, putting it in a new column for itself, right? And this cell and this cell, sorry. This cell, putting it into a new cell, right? And then we have a whole new column here. Okay, what do I do with that then? What do I do with that? Okay, well then all I would do is calculate the mean and the standard deviation of this column, right? So what I would do is I would just calculate the sum of this column, right? And that's going to be something, right? That's going to be something. So I'm going to add up this column divided by how many there are, and that's going to give me the mean of this column, right? Of this column. Now we know that this represents the difference, right? The math here, sort of the process, does not differentiate. It doesn't care. It's just numbers, right? To the math. But to us, we know that what we're working with is this column of differences. And then we also would just find the standard deviation, which is, let's see, the square root of, let's see if I can remember this. Yeah, where it's just, let me write it like this. Sum of xi minus the mean squared divided by n minus 1, and that's all underneath the square root. Okay, cool. So then I would just find that. We've done that before too, of this column of differences. We're treating it as if it's just all alone, as if it's totally independent, right? Totally just out there by itself. Some new column of data, okay? And then what do I do? Well, I've got this the sample mean and the sample standard deviation of this one column. And then what I'm going to do is, since over here in the paired t world, our null hypothesis is that the one population is the same as the other population, right? That means there's no difference between the two. Well, we can also rewrite that as mu1 minus mu2 equals 0, right? Effectively, what we're doing is we're just moving this over here, right, doing a little bit of algebra, and we find that our null hypothesis can also be written as this, where when you subtract the two, that means that there is no difference. The difference equals 0, okay? Well, why don't we just take that value and chuck it on over here as our mu naught, right? So we know that this whole column here represents the differences. We found the mean of the difference, right, just on this column by itself. We've also found that column standard deviation, right, that sample standard deviation. And let's just plug in 0 for mu. And then after that, we do a one sampled t-test, right, with a known mu naught of 0, right? Because effectively, functionally, that is what we're doing over here, right? Where the math behind the scenes for this, gross, right? I don't want to take the time to do it. But we already know, I don't want to take the time to do it because we already know how to do this. We already know how to find this much easier sample standard deviation based on, this one column. You find your test stat, right? The standard error formula is just the sample standard deviation divided by the square root of how many things there are, right? Which is just 2, right? So the square root of 2. Degrees of freedom, n minus 1. You can think of it either as the n of the column or the n of the pairs, whatever. It's going to be the same, right? So in this case, it would be 2 minus 1, so 1 degree of freedom, right? Kind of a clunky example. And then the confidence interval, just take your denominator for the standard error, find the t-crit as you would normally for a one sample t-test, and then you're set. Oh my gosh, this blew my mind when I learned it. And I was like, I wish I learned this earlier, right? Way back when, because this is so much easier than doing, this whole process over here is fine, but it's this little mother that makes things very difficult, right? Or at least not even difficult, it's not even the right word to use, just so tedious. And there's a ton of room to make mistakes when you're calculating this thing. But when you're doing this, when you're framing things as a one sample for the difference, easy peasy, right? Much easier to kind of work with, right? So that's the general idea. And let me kind of erase this, just so we're all, it's all clean here. Actually, I will keep that. That's important. Okay. Turns out that once you do this one sample t-test, you're going to get the same freaking thing. You're going to get the same dang thing, which is awesome, I think. This is much easier to do if you're not supplied with these two things, right, than doing the actual math for the paired data, right, for the paired t-test. Okay, very cool, very cool. So that's pretty much that. Let me think. Is there anything else I wanted to say about this? I don't think so. Oh, yeah. Well, so in the homework, there is one bonus question that does this, right? So the first question, it's about airline pilots and like reaction time or something like that. Real data. It's real data. The first example is that you're given the difference and the sample standard deviation of the differences, right? And then all you have to do is plug and chug. But then I actually give you, in a bonus question, so you don't have to do it, right? If this totally flew over your head, no worries, right? But as a bonus question, for a couple extra points, hey, wink, wink, nod, nod, whatever, I give you the actual data, and it's 10 data points long, okay? So all you need to do is just follow these 3 steps, and then you're set, right? Where the most, this is going to be that'll be a little bit long to calculate, but so long as you keep everything ordered, you're going to be totally set, right? So I really recommend that you do try this. Because you'll get the same thing. You will get the same thing within probably some rounding things, okay? So if you don't, then double check and you made sure you did this right. Or, if you feel like you did this one right, then go double check and make sure you did this one right. Woof, boy, just so many different things you can do with this, right? So we get back to this idea that all these things are related in some way. And then with this specific instance with paired data, right? one time point to the other with the same people or the same places, whatever, you can kind of cheese out. You can kind of work the system a little bit and do a one sample t-test, and that's totally legitimate, which is great. Okay, so with that, for real, I think that's it. Unless I have another kombucha idea, then you'll be hearing from me in just shortly after this video, but I don't think so. So with that, I will see ya when I see ya.